An electrolyte solution conducts electricity. A weak electrolyte solution does not conduct electricity well, while a non-electrolyte solution does not conduct electricity at all. Electrical conductivity requires the presence of ions in solution, and the more ions present, the greater the electrical conductivity. Salts are ionic compounds and all dissolve in water to produce electrolyte solutions, though their solubilities differ. Molecular compounds do not form ions and are made up of nonmetal atoms. When the compound is dissolved, the entire molecule stays intact. This means that the solution will not conduct electricity. Some compounds which appear to be molecular do form ions. The 6 strong acids ionize completely in solution, and weak acids also form ions to a limited extent. When dealing with solutions, we often have to account for dilution. In this example, we need to find the resulting concentration when a 25 milliliter solution of 0.125 molar hydrochloric acid is diluted to 1.0 liters. The CIVI equals CFVF equation is the relation between the initial concentration and volume, and the final concentration and volume. This can be derived by beginning with initial moles equals final moles. This works because adding water will not change the moles of solute. Since concentration times volume is equal to moles and the initial and final moles are equal, the initial concentration times the initial volume must be equal to the final concentration times the final volume. In this case, our initial concentration is 0.125 moles per liter and the initial volume is 25 milliliters. We have the final volume, which is 1 liter. If we plug these values into the equation, we can find the value of the final concentration. Before doing the calculation, we could also have rearranged the equation to isolate the final concentration. This form, which has the final concentration equal to the initial concentration times the dilution factor, will be very useful in all remaining chapters, as anytime solutions are added to one another, they dilute each other. Don't forget that doubling the volume always halves the concentration. The dilution factor is the initial volume over the final volume, but if you have trouble remembering this, you can always rederive it from the CIVI equals CFVF equation. Now let's try calculating the concentrations of ions when we mix two solutions together. We have mixed together 55 milliliters of 0.22 molar ammonium sulfate with 25 milliliters of 0.45 molar ammonium sulfide. It is always a good idea to begin by writing the chemical equations, but we could also deal with the concentrations first if we wanted to. Both ammonium sulfate and ammonium sulfide are soluble and will dissociate in solution. When one solution is added to another solution, both are diluted. This means we have to calculate the concentrations of ammonium sulfate and ammonium sulfide using the dilution factor. The final volume is the total volume when the solutions are added. In this case, we add 55 milliliters to 25 milliliters to get a final volume of 80 milliliters. Once we have the final concentrations, we can write them under the chemical equations, using the mole ratio to relate the concentrations to each ion. There are 2 sources of ammonium ions here, so we have to add the 2 concentrations together. This gives us 0.58 moles per liter for our ammonium concentration. Solutions consist of some solute dissolved in a solvent. As we keep adding solute, there comes a point where no more solute will dissolve. We then say that the solution is saturated, meaning no more solute will dissolve and there is some undissolved solute present. This means that solid salt will be seen in the container. Sometimes the concentration of a solution can be increased beyond its saturation point, which is known as supersaturation. Solubility is defined as the maximum amount of solute that can be dissolved in a particular volume of solvent. There are several different units for solubility which are listed below. Let's go through a brief overview of the units of concentration. Molarity is moles of solute per liter of solution, in units of moles per liter or capital M. Concentration can also be expressed as a mass or volume percentage. The mole fraction is another important form of concentration, where the moles of one substance are divided by the total number of moles. It is written as a decimal, not a percentage, and is unitless. Molality, not to be confused with molarity, is moles of solute per kilogram of solvent. Note that it is per kilogram of solvent and not per kilogram of solution. Molality is no longer tested on the AP exam. In a saturated solution, an equilibrium exists between the undissolved solid and the dissolved ions. This is not a static equilibrium but a dynamic one because it is a continuing process. The forward reaction rate of dissociation or dissolving equals the reverse reaction rate of crystallization or precipitation. The equilibrium in a saturated solution of lead-2 chloride can be represented by the equation shown below. Always place the solid on the left side of the equilibrium. Also, when writing the equation for an equilibrium, remember to use the double arrows rather than a single arrow. When a salt is added to water, it will dissolve if the attraction of the cation and anion to each other is overcome or replaced by an attraction of the ions to a polar water molecule. For instance, when sodium chloride is placed in water, the attraction of the sodium cation to the chloride anion is replaced. The cation is attracted to the negative dipole on the oxygen atom of the water molecule, while the anion is attracted to the positive dipole on the hydrogen atoms of water. Dissociation occurs because the ions are more attracted to the solvent than to each other. However, when a salt such as silver chloride is placed in water, the silver cation is more strongly attracted to the chloride anion, and that attraction can only be slightly overcome by an attraction to water molecules. This means that most of the silver chloride solute remains undissociated. However, we should note that the silver chloride is not insoluble. A small amount of silver chloride will dissolve. This is one example of a solubility table. The term soluble means that more than 0.1 mole of salt will dissolve in 1 liter of solution. Low solubility does not mean that the salt does not dissolve. It just means that less than 0.1 mole of salt will dissolve in 1 liter of solution. Salts with alkali ions, ammonium or nitrate, are soluble. Acids are also soluble. Salts with halides or sulfate are usually soluble except for some important exceptions. Salts containing sulfide, hydroxide, phosphate, carbonate, or sulfite usually have a low solubility except for some exceptions. There are 3 types of equations used to represent double replacement reactions. A formula equation shows the chemical formulas of the compounds and their states. You would use the solubility table to identify the product with low solubility. In a complete ionic equation, the soluble salts are represented in their dissociated form. Strong acids are also shown in their ionized form. All other substances appear in an ionic equation in the same format as they do in a formula equation. Because the precipitate has low solubility, it is not shown dissociated. So, to summarize, look for 2 things: soluble ionic compounds and strong acids. These should be dissociated or ionized. Everything else should be left alone. In other words, written in the same form. In a net ionic equation, only the ions that take part in the reaction appear. Spectator ions are ions that are all the same on both sides of the equation, and are not shown in the net ionic equation. In this example, the sodium and sulfide ions are the same on both sides of the reaction, and are thus spectators. Qualitative analysis refers to any procedure that can be used to help identify unknown ions in solution. Looking at the color of a solution is one method of identifying ions. For example, solutions containing copper-2 ions are blue, and permanganate is a deep purple color. Flame tests can also help identify the ions present. Copper-2 ions turn a flame a blue-green color, while lithium ions will turn it red. Selective precipitation is an important method for indicating the presence of unknown ions. The color of the precipitate, the amount formed, or the speed at which it forms can also help identify the ions present. The solubility rules can be used to design a qualitative analysis scheme to determine the identity of ions in a solution. There are different ways to go about showing this, but the scheme should list steps, including the compounds that you are adding to precipitate one ion at a time, and how you will remove the precipitate from the solution. In this example, we need to design a process to individually remove bromide, sulfate, and sulfide ions from a solution. Let's begin by taking a look at the solubility table. Sometimes it's best to begin by precipitating out the ion that is soluble with the lowest amount of substances, but there are many different paths we can take. It looks like bromide and sulfate are soluble with most cations, but sulfide is not. Maybe we could remove sulfide first by adding a metal ion that bromide and sulfate will both be soluble with, like a chromium or iron ion. Then we could precipitate the sulfate by adding barium or calcium ions. Adding silver or lead-2 ions wouldn't do us much good if we were trying to separate the sulfate and bromide, because sulfate and bromide both form precipitates with them. But once we've removed the sulfate, we could definitely use them to precipitate out the bromide. Alternatively, we could have removed the sulfate first by adding calcium or strontium ions, and then dealt with the sulfide and bromide after. There are many different methods that would work. Keep in mind that we aren't adding in these cations as isolated species. The cations and anions we are adding need to be in the form of soluble compounds. For instance, if we wanted to add calcium in to precipitate out some anion, we wouldn't just be adding in calcium ions alone. We would add something like calcium nitrate, so calcium nitrate would be the source of the calcium ions. One way to approach this question is to use a flowchart. First, we can precipitate out the sulfate ion by adding calcium nitrate, because calcium sulfate will precipitate. Bromide and sulfide ions form soluble compounds with calcium, so they will not precipitate. The calcium sulfate precipitate can then be filtered out. Next, we can add copper 2 nitrate to precipitate out the sulfide. The bromide can then be removed by precipitating it out with silver. Here is an alternate method of representing what we just did. The steps list the reagent added and the resulting precipitates. Another way to remove the precipitate would be to centrifuge so the precipitate settles and then decant off the supernatant solution which contains the remaining ions. Sometimes there could be more than one ion present in solution that could be responsible for the precipitate. For example, if we added silver ions to a solution that might contain chloride and iodide, we would be unable to conclude if the precipitate was silver chloride, silver iodide, or both silver chloride and silver iodide. Adding a concentrated solution of ammonia to the precipitates would cause the silver chloride to redissolve, but the silver iodide would remain as a precipitate. Silver chloride is actually a white precipitate and silver iodide is light yellow, so color could also be of use in this particular case. A few examples of reagents that can dissolve some precipitates are shown here. Adding ammonia to silver and copper 2 precipitates will dissolve them because both cations will form soluble amine complexes. Carbonates are another example of precipitates that can be dissolved easily. The addition of a strong acid will cause the carbonate precipitate to dissolve, forming water and carbon dioxide. Hard water refers to the presence of calcium, magnesium, or iron 2 ions in water at relatively high concentrations. Soft water is water that does not contain these ions. In many parts of the world, there are significant amounts of limestone, calcium carbonate, in the soil. When carbon dioxide from the atmosphere dissolves in water from streams or rain, this solution dissolves limestone. The presence of the calcium ions in the water supply poses hazards for municipal water systems and homes. The carbon dioxide is driven off as a gas as the water is heated. This leads to the formation of a scale of calcium carbonate in water heaters, pipes, kettles, and boilers, which can result in lowering the efficiency of heating systems and even the blocking of water pipes. Soaps also react with calcium and magnesium ions to form soap scum. The addition of calcium oxide or sodium carbonate to underground water reservoirs to precipitate out calcium and magnesium ions is one treatment for hard water. Additionally, some home treatment systems use ion exchange resins that attract calcium and magnesium ions to the resin surface and release sodium ions. In a saturated solution, an equilibrium is established between the dissolving and recrystallization of a salt. For example, a dissociation equation for the equilibrium of lead 2 chloride would look like this. If we set up a KEQ expression, there is nothing in the denominator since the reactant is a solid. Solids and liquids are not included in these expressions due to them having constant concentrations. Since this is a special kind of equilibrium, it gets its own equilibrium constant, KSP. KSP is the solubility product constant. Recall the definition of molar solubility. The molar solubility of a substance is a molar concentration of solute in a saturated solution. The solubility product constant, KSP, is the product of the ion concentrations in a saturated solution raised to the power of the coefficients in the equilibrium. KSP of a compound is constant at a constant temperature. In other words, the only thing that can change KSP of a substance is the temperature. While the solubility of a substance differs from its solubility product constant, they are related and we can calculate one from the other. In these types of problems, it is often best to start by writing down the equilibrium equation for the saturated solution. We should also write down all the information we know in the problem, which usually means writing the concentrations below the equations. Next, we can write the KSP expression down. After that, we should be good to plug in values and solve the expression. Let's try this method. The solubility of lead 2 chloride is 4.4 grams per liter at a particular temperature. What is its KSP? Well, we can start by writing down the equilibrium equation for lead 2 chloride, remembering to use the double arrows. We have a concentration, but it is in grams per liter and we need it in moles per liter. Once we add the concentration, it helps to write it under each species in the equilibrium equation, using the mole ratio to relate it to the compounds. Next we can write the KSP expression. The concentration of each ion is raised to the power of its coefficient in the equilibrium equation. This means we must square the chloride concentration. We have all the values we need, so we plug them into the equation and get a value for KSP. The solubility product constants of salts can be found in tables like this one. It is important to remember that the KSP values are not concentrations. However, if we are looking at different salts that are the same type, like AB, AB2, and AB3, which are general empirical formulas used to indicate the cation to anion ratio, then we can use their KSP values to compare the relative magnitudes of their solubilities. For example, let's list the compounds potassium chloride, barium chromate, and silver iodide in order of solubility from lowest to highest. Potassium chloride is soluble since it contains an alkali metal, while the other two compounds have low solubility. Barium chromate and silver iodide are both AB salts, so we can use their KSP values to compare their solubilities. Silver iodide has a lower KSP than barium chromate. Therefore, from lowest to highest solubility, we have silver iodide, barium chromate, and potassium chloride. Calculate the solubility of iron 2 hydroxide from its KSP. What mass is dissolved in 250 milliliters? This is a two-part problem, and we will begin by calculating the solubility. We don't have molarities to include under the equilibrium expression, so we represent them using a variable. S is equal to the molar solubility of iron 2 hydroxide. Since there are 2 moles of hydroxide for every mole of iron 2 hydroxide, the concentration of hydroxide will be 2S. Next, we write our KSP expression. We plug in the unknown concentrations of the iron 2 ions and hydroxide, and we get the KSP value off of a table if it is not given to us. We then solve for S, which is the solubility of iron 2 hydroxide. Next, we want to find the mass of iron 2 hydroxide that has been dissolved in 250 milliliters. We have a volume and molarity, so we just need to quickly calculate the molar mass of the compound to get our mass value. As we have seen from our KSP table and examples, there are different kinds of salts. Here is a quick summary of some of the types of salts and how their KSPs relate to their solubilities. For type AB salts, the KSP is equal to S squared. For AB2 or A2B salts, it is 4S cubed. We can figure this out for other kinds of salts as well, such as AB3 and A2B3. Now we will examine situations in which the ions forming the precipitate do not come from the same solute. This means that the concentrations of the ions in solution are not related to one another, but instead depend on the concentrations and the volumes of the solutions being combined. It is always important to consider the source of each ion when determining their concentration. The KSP value represents the maximum product of the ion concentrations in a saturated solution. If an equilibrium is not present in the solution, then we calculate a trial ion product, TIP, also called trial KSP value or reaction quotient Q. If the TIP is greater than the KSP, a precipitate forms. In other words, if the product of the ion concentrations present is greater than the KSP value, the ions will not remain dissolved in solution and a precipitate will form. If the TIP is smaller than the KSP, no precipitate forms. If the TIP equals the KSP, the solution is saturated. This occurs when a precipitate is just beginning to form. Will a precipitate form when 23 milliliters of 0.020 molar sodium carbonate is added to 12 milliliters of 0.010 molar magnesium chloride? We can start by writing down the double replacement reaction between both reagents, which allows us to determine the precipitate that will potentially form. Then we write an equation representing the equilibrium present in a saturated solution. Since we are adding two solutions together, the concentrations will be diluted. We multiply the initial concentrations by the dilution factor to get the concentrations of the ions right before the reaction. Remember to consider the source of these ions. Carbonate has a 1:1 mole ratio with sodium carbonate, and the magnesium ions have a 1:1 mole ratio with magnesium chloride. Next, we write the KSP expression so we can calculate the value of the TIP. After plugging in the concentrations, we get a value of 4.4 times 10 to the negative 5. This is larger than the KSP value of 6.8 times 10 to the negative 6 we get off of our table, so a precipitate will form. What mass of sodium sulfate is required to start precipitation in 500 milliliters of 0.030 molar calcium chloride? Once again, we write the double replacement reaction to determine the possible precipitate. Before we add any sodium sulfate, our solution contains 0.030 molar calcium chloride. By writing the dissociation equation of calcium chloride, we can relate the molarity of the calcium chloride to the molarity of calcium ions. Next, we write the KSP expression. We want the TIP to equal the KSP, which it does when a precipitate is just beginning to form. We know the concentration of calcium ions and we get the KSP off of the table. What we need to find is the concentration of sulfate that will lead to precipitation. We get a value of 2.4 times 10 to the negative 3 moles per liter for the concentration of sulfate, which is equal to the concentration of sodium sulfate because the mole ratio between sulfate and sodium sulfate is 1 to 1. Now we can use the volume, the concentration we just determined, and the molar mass of sodium sulfate to get the grams of sodium sulfate required to start precipitation. As always, remember to pay attention to significant figures. What is the maximum concentration of sulfate that can exist in a saturated solution of calcium carbonate? We first write the equilibrium equation for calcium carbonate, but we don't know the concentration of calcium and carbonate yet. To figure this out, we use the KSP expression. Now that we have the concentration of calcium ions in a saturated solution of calcium carbonate, we can figure out the maximum concentration of sulfate that can exist in the solution. We write the equilibrium equation for calcium sulfate to help us set up the KSP expression. The product of the calcium ion concentration and the sulfate concentration will be equal to the KSP when the solution is saturated. If we plug in the KSP value and the concentration for the calcium ions that we just calculated, then we will get the maximum concentration of sulfate that can exist in the solution. The solubility of a substance depends on the presence of other ions in solution and the temperature. The KSP of a substance depends on temperature only. Let's look at the example of magnesium carbonate. Adding magnesium ions at constant temperature will increase the concentration of magnesium ions, resulting in a left shift. We can also see this when we look at the KSP expression. The temperature is constant, so KSP is constant. Since the product of the concentrations of the ions must remain constant as well, as the concentration of magnesium ions increases, the concentration of carbonate decreases. As we can see, the solubility of a solute is decreased by the presence of a second solute in a solvent containing a common ion. This is known as the common ion effect, which refers to a situation where a dissolving salt is added to a solvent containing an ion in common with a dissolving salt. According to Le Chatelier's principle, the solubility of magnesium carbonate may be increased by removing the magnesium or carbonate ions. This would cause the equilibrium to shift right, increasing the solubility of the solute. Precipitation is one common method of removing ions. Neutralization and complex ion formation are other methods. For instance, adding concentrated ammonia will dissolve silver or copper 2 precipitates. What is the solubility of magnesium hydroxide in A, water, and B, 0.10 molar magnesium chloride? To find the solubility in water, we write the equilibrium equation and the KSP expression. We solve for S, which is equal to the solubility of magnesium hydroxide in water. Next, to find the solubility in 0.10 molar magnesium chloride, we should recognize that this is an example of the common ion effect. The equilibrium for the saturated solution will be shifted by the addition of the common ion magnesium from the magnesium chloride. After writing the equilibrium equation, we create an icebox. The initial concentration of magnesium ions is 0.10 moles per liter, while the initial concentration of hydroxide ions is 0. The amount of magnesium hydroxide that dissolves will increase the magnesium and the hydroxide ions by x and 2x respectively. We assume that one number is negligible with respect to another if one number is less than 5% of the other. For now, let's assume that the amount of magnesium ions that dissolves from the magnesium hydroxide is very small compared to the amount of magnesium ions in solution from the magnesium chloride. We need to state our assumption that x is negligible. We then write the KSP expression and plug in the values from the ICE table. Our value for x is equal to the solubility of magnesium hydroxide in 0.10 molar magnesium chloride. Since 3.7 times 10 to the negative 6 is certainly less than 5% of 0.10, our assumption that x was negligible with respect to 0.10 was valid. Let's do another common ion effect calculation. Solid calcium sulfate is added to 1 liter of a 0.1 molar solution of sodium sulfate until no more calcium sulfate will dissolve. If the KSP for calcium sulfate is 2.45 times 10 to the negative 5, what is the calcium ion concentration in the saturated solution? Let's start by writing the equations down to get a better sense of what is going on in the question. We have sodium sulfate and calcium sulfate, so it doesn't look like we'll have any kind of double replacement reaction. Sodium sulfate is soluble, so we can write the corresponding dissociation equation. Calcium sulfate, on the other hand, has a low solubility, so we will write the equilibrium equation for it. Now we should write down what we know. We have the concentration of sodium sulfate, thus the ions it dissociates into. The concentration of the ions from the calcium sulfate is unknown. The KSP expression is going to be for the solid calcium sulfate, so we can write that down. We could use a nice table like we did in the previous example, but the equations alone are sufficient for filling in the KSP expression. We only have one source of calcium, the calcium sulfate. The concentration is unknown and equal to x. On the other hand, we have two sources of sulfate. We have the concentration of x from the solid calcium sulfate that was added, and a concentration of 0.1 molar from the sodium sulfate. However, we will assume that x is negligible with respect to 0.100. Remember that we need to state this. We then use the KSP value that was given to solve for x. X is equal to the concentration of calcium ions, so we have our answer. Let's quickly check to make sure our assumption was valid. 2.45 times 10 to the negative 4 is about 0.245% of 0.100. So assuming x was negligible was indeed correct. Most of the time this will be the case. But what if x wasn't negligible? This question is set up like the previous one, except that we have a lower initial concentration of sodium sulfate. This time x is over 5% larger than 0.0150, so our assumption was not valid. If we assume that x is not negligible, then we get a quadratic equation. To solve this, we can use the quadratic formula. If you do have to solve a problem this way, then you should indicate it. When we plug our coefficients into the quadratic formula, we get two values for x. We can discard the negative one since we expect concentration to be a positive value. Notice that this answer is different from the one we got when we assumed x was negligible. Be aware that calculations involving the quadratic equation no longer appear on the AP exam. The rest of this video will delve into colligative properties, but this content is no longer required for the AP exam. Raoult's law illustrates how the presence of a non-volatile solute lowers the vapor pressure of a solvent. To get the vapor pressure of a solution, the mole fraction of the solvent in the solution is multiplied by the vapor pressure of the pure solvent. Remember the relationship between different units of pressure, as these calculations may involve converting between them. This question asks us to find the equilibrium vapor pressure of a solution of sucrose in 845 grams of water at 100 degrees Celsius. The equilibrium vapor pressure of water at 100 degrees Celsius is 760 torr. In this case, the water is the solvent and the sucrose is the solute. We can use the molar masses of both compounds to find the moles because we will need the moles for the mole fraction. Remember that it is the mole fraction of the solvent and not the solute. Thus, we should have the moles of water in the numerator and the total moles in the denominator, which is just the moles of water and sucrose added together. Once we get the mole fraction, we can multiply it by the vapor pressure of pure water to get the vapor pressure of the solution. A pressure lower than the vapor pressure of pure water makes sense. Solute particles take up space on the surface of the solution, meaning that there are less sites for the water molecules to evaporate from. Fewer water molecules are able to enter the vapor phase, resulting in a lower vapor pressure of the solution. Keep in mind, this is all assuming that the solute is non-volatile. Colligative properties are the properties of a solvent that are changed by adding a solute. They depend on the number of solute particles and not the identity. For instance, the boiling point of a solution is elevated by the addition of a non-volatile solute. This equation describes the relationship between the molality of a solution and the magnitude of the temperature change to the boiling point. Kb is the molal boiling point elevation constant in units of degrees Celsius kilograms per mole. The molality used in the equation is that of the solute. The Van Hoff factor depends on whether or not the solute is an electrolyte. It relates to the number of particles in solution formed by the solute. For example, molecular compounds stay intact in solution and thus will have a Van Hoff factor of 1. Sodium chloride would dissociate into two ions, sodium and chloride, so it will have a Van Hoff factor of 2. Potassium sulfide would dissociate into 3 particles and will have a Van Hoff factor of 3. Freezing point is lowered by the addition of a non-volatile solute. The equation is pretty much the same except there is a different constant for freezing point depression. The constant depends on the identity of the solvent. Also, note that the product of the molality and the Van Hoff factor is known as the effective molality. This can be useful when comparing the change in boiling or freezing points caused by different solutes. One way to remember that the boiling point is raised and the freezing point is lowered is that the addition of a solute essentially extends the liquid range of a solution. We can also recall why they put salt on the roads in wintertime. It prevents ice forming because it lowers the freezing point of water. For water, the molal boiling point elevation constant is 0.51 degrees Celsius kilograms per mole, and the molal freezing point depression constant for water is 1.86 degrees Celsius kilograms per mole. Another colligative property is osmotic pressure, which is the pressure that just stops osmosis through a semi-permeable membrane. To understand what this statement means, let's look at this U-tube which contains a pure solvent and its solution, separated by a semi-permeable membrane. The solute particles are non-volatile and cannot pass through the membrane, but the solvent particles can. Because the solute particles interfere with the passage of solvent from the solution, the rate of transfer is slower from the solution to the solvent than from the solvent to solution. As more and more solvent particles travel to the solution volume increases. This results in an extra pressure which pushes the solvent molecules back to the solvent. Eventually, enough pressure will build up so that the system is in equilibrium and the rate of solvent transfer is the same in both directions. Applying an external pressure to the solution can prevent the flow of solvent into the solution. The osmotic pressure of the solution is equal to the minimum pressure required to stop the osmosis. The dependence of osmotic pressure on the concentration of the solution is shown by this equation. The pi symbol represents osmotic pressure. We use the constant R, which is 0.08206 liter atmospheres per mole Kelvin. Note that the osmotic pressure also depends on the temperature and the Van Hoff factor. Let's try a freezing point depression and boiling point elevation question. 200 grams of propylene glycol is dissolved in 400 grams of water. What are the freezing point and boiling point of the solution? We'll start by finding the freezing point of the solution, so we write down the equation for freezing point depression. We use the Kf value of water, which is 1.86, and since the solute will remain intact in solution, the Van Hoff factor is 1. The molality is moles of solute divided by kilograms of solvent. We can use the molar mass of propylene glycol obtained from the molecular formula to find the moles in the solution. We also convert the grams of water into kilograms by dividing by 1000. We get a value of 12.2 degrees Celsius, but we want to find the freezing point of the solution, so this is not the final answer. Since we know that the presence of a non-volatile solute will lower the freezing point, and the freezing point of pure water is 0 degrees Celsius, we subtract 12.2 from 0. This gives us a freezing point of negative 12.2 degrees Celsius. The calculation for the boiling point is similar, although we have to use the Kb constant instead of the Kf1. The boiling point will be elevated, and the boiling point of pure water is 100 degrees Celsius, so we add our temperature change to 100 degrees Celsius. Freezing point depression, boiling point elevation, and osmotic pressure can each be used to determine the molar mass of an unknown solute. In this case, 30 milligrams of a protein is dissolved in 35 milliliters of solution. The osmotic pressure is 0.56 torr at 35 degrees Celsius. We are given the osmotic pressure, so we will use the osmotic pressure equation. We have the mass of the protein but not the moles. The molarity will help us find it. The molarity of the solution is the only unknown in the equation, so we rearrange the equation to isolate it. We then plug in our known values into the equation. We must be careful with the units here. The R constant we are using is in terms of atmospheres, so we must convert our osmotic pressure from torr to atmospheres. Additionally, we need our temperature to be in kelvins. The Van Hoff factor is 1 because the protein is a molecular compound and will stay intact in solution. Now that we have our molarity, we can use the volume of the solution to find the moles of the solute. Dividing the mass, which has been converted from milligrams to grams, by the moles of the protein yields the molar mass of the protein. 29,000 might seem like a large number, but this is reasonable for a protein. What we don't want is a molar mass that is less than 1, as hydrogen is the lightest element and has a molar mass of 1 gram per mole.